Hi, I'm Heino Falke from Radboud University, Nijmegen in the Netherlands, and I want to talk to you about some shady business concerning black holes. What is it that the Event Horizon Telescope has seen in M87? Now, to understand that, we need to understand light bending. And this was actually discovered and calculated already very early. In 1916, David Hilbert calculated in a lecture how light would be bent around black holes. And that was written up by von Laue later, a few years later in this book. And when light comes in tangentially to a black hole, there's a certain impact parameter. It will actually be bent and can end up onto a circular photon orbit where it will in principle remain forever. That photon orbit has a radius of 3.5 short-circuit radii, 3 gravitational radii, which is gm/c squared. And that means that all the light that comes in between this separation here at these impact parameters, which has a size of a diameter of about 5 short-circuit radii, all the light that comes in here will actually end up in the event horizon. All the light that orbits or impacts at a slightly larger separation will in fact go around the black hole and escape to infinity. And that will create a sharp boundary, a watershed for light, so to speak. It also means that if you're near the photon orbit and you have an isotropically emitting light source, half of the light will actually be able to escape to infinity, while the other half of the light will end up in the event horizon. And once you move the source from the photon orbit towards the event horizon, your loss cone, your escape cone, will become smaller and smaller and approach zero at the event horizon. And so everything in between the photon orbit and the event horizon will fade away rather quickly as it moves towards the event horizon. This is so-called, what I call the twilight zone of black holes. Now, the light bending will make all the structures around the black hole look distorted, bent, obviously. And this, has created that image of black holes in our minds based on these early calculations, which are reminiscent of thin accretion disks. So what you see here is a calculation by Cunningham and Bardeen, where they calculate just the position of a star on a circular orbit around a black hole. And you see how that orbit will be bent. And that already looks like an accretion disk, which was calculated in the late 70s by Luminet, a thin accretion disk, which is more or less stimulated, motivated by the discovery of quasars, where the idea was that you'd have a standard thin accretion disk, which is radiatively, optically thick and radiates very, very strongly. And what you see is, again, the strong bending. You see the absorption here by the foreground absorption by the disk. You see here a dark region, and that dark region is actually the whole of the accretion disk, which is thought to terminate at the ISCO innermost stable circular orbit and deformed. So you don't see a nice circular feature as we see in M87. You see like a half ring. And in this simulation, you see a little tiny ring in here as well. And that is actually going around this lensed photon ring where light is going around in a circle. This is essentially a projection of the inner edge of the accretion disk that goes around once, in fact, multiple times around the black hole. Now, if you look Hollywood movies, then you recognize all these pictures. Again, thin accretion disk, optically thick, geometrically thin. That's interstellar, and even NASA shows a black hole still in the same way. Thin, optically thick, but now in a red color. And I think that's maybe a trend that we've set with the EHT to give it a red color, which in fact is based on some of the early predictions that we made in 2000s. Now, the astrophysical reality is slightly different. This here is a spectrum, a spectral energy, no, actually a spectrum of Sagittarius A star. In fact, the spectrum of M87 doesn't look fundamentally different. The idea is that you have a black hole which is surrounded by an accretion flow which is optically thin and which doesn't radiate too much. In the case of M87, it's quite clear that we have a jet outflow. In Sagittarius A star, that's still debated. At least in our simulations, we always see jets coming out. And the innermost region, the foot point of the jet, the innermost accretion region, that's where emission is produced at the highest frequencies. And then when you have an outflow, then the emission will emit at lower and lower frequencies. And so what you need to do is, if you have a spectrum like this, which is a flat spectrum, you have to go to the highest frequency in the flat spectrum before it actually cuts off. This is near the event horizon. And there the idea is that the black hole is actually, if it's a jet, for example, or an ADAF, it's actually engulfed by this emission, which is also optically thin. So it's geometrically thick, optically thin. You have radiation from all around. And this is something that is dependent on astrophysical parameters, namely the mass and the accretion rate. We are here talking about low luminosity AGN, where this model applies, which is actually the majority of black holes in the universe are low luminosity. And the peak frequency, where this turnover happens from where you approach the event horizon. This also depends on mass and accretion rate. In a very simple model, you can do this in the back on the envelope in a Blandford-Kernigel type model, you'll find that the accretion rate, the higher the accretion rate, the higher the turnover frequency, and the larger the black hole mass, the smaller, the lower the frequency is. So what happens if you have a spectrum like this? Here you have to look maybe in the millimeter regime to get near the event horizon. If you go to an X-ray binary where the black hole mass is much, much smaller, also the accretion rate is smaller, but actually the mass enters with a higher power. So that means that the flat spectrum extends to higher frequencies, and then the event horizon region frequency, the characteristic frequency, would be in the optical or near-infrared regime. So you pick your right frequency. And for M87 and Sagittarius A star, the two main targets of EHT, it's a pure coincidence. And if you see, look at the accretion rate differences, these are 5 orders of differences. But to a power 2/3 gives you a factor 2000. If you go to the mass difference, is also factor 2000, now linear, and that actually cancels in this equation. So that's why the characteristic frequency you need to look at for M87 and Sagittarius A star is at the same wavelengths, despite the fact that mass and accretion rate are so widely different. And this is just a function of this fundamental plane relations that we developed a couple of years ago, which allows you to couple radio and X-ray emission and the peak frequency in the SED to black hole mass and accretion rate. And that seems to work amazingly well over large areas of the parameter space. Now, how does a black hole look if you have extended emission? The first clue came from this paper by Bardeen in '73, where he was calculating a black hole in front of a star. You just have a black hole in a double system, for example, pass in front of a star. And then what struck me was we had this small black hole, but it was then suddenly surrounded by this big region where light was actually stamped out, which was lacking, a dark silhouette, you might say. And the interesting thing is that was for a highly spinning black hole. So a spinning black hole has a very small event horizon of one gravitational radius, but the diameter of this entire silhouette here is a factor 10. So it's 10 gravitational radii more or less, even for a highly spinning black hole. And that was, very stunning. Now it turns out the picture here is not quite correct. What he was calculating, which was something that Gralla showed, this here is actually the Bardeen size. The dark region you would see is actually slightly larger. Why? Because light doesn't need to end up in the event horizon to see darkness. It's enough if your line of sight will be bent around by 90 degrees, then you actually look next to the star, and you see the dark universe. So you don't see the black hole, you see the dark universe. So what you see in the central region is black hole, and this here is the entire rest of the universe projected into a dark annulus around the black hole. Now, that changes if you go to this picture I just described, where you have emission surrounding the black hole entirely, optically thin emission around the black hole. And then actually this dark annulus disappears. Why? Because wherever your light goes around the black hole, there's always light that fills in that annulus. Only if it hits the event horizon, you actually get a dark region. And so this was a picture here we had in the late 90s. You had an accretion flow and a jet, and it would engulfing the black hole. And that would then produce what we called a dark shadow. Not a silhouette, a dark shadow, because you're not going to see a sharp dark feature. You have emission in front and behind, and so the emission in front will actually fill in the dark region. So the shadow is a bit less sharp in that sense than the shadow is, than a silhouette is. What we did is we calculated different models of astrophysical models, so spherical inflows, rotating, non-rotating, or even cylindrical jets-like structures. Now, in all cases, you would see that shadow, not completely dark, but still very sharply defined here, and then sometimes surrounded by this ring of light, this light ring. And that light ring is actually a projection of all the emission surrounding it. The shadow itself is the absorption feature of the event horizon. And so the nature of the black hole hides behind the shadow, and all the emission hides in all the astrophysics hides in the light ring. The interesting thing is that this shadow feature actually depends very little on shape or orientation. So this here are different inclinations for a highly spinning black hole, and you see, it becomes circular if you look down the axis, and it gets a little dent if you look from the side. Same as if you have spinning, very highly spinning, it gets a little dent, and if it's short, it's completely spherical. And that dent, gives you sort of a less than a 10% dent from circularity, and the size changes only by 5%. And that makes the shadow such a strong prediction for a black hole. It's a very characteristic feature that you need to have. If you don't have within 10% that dark shadow, then there's something wrong with your model. And so it was a clear prediction. What we needed to see was this dark region. Now, how much does it depend on astrophysics? As long as you are geometrically thick and engulfing everything, it's actually a fairly robust feature. Here, this is a simulation that Ramesh Narayan did and his team. In fact, surrounding a black hole with a emitting region, but then evacuating the central region, creating an artificial hole, like the hole in the accretion disk I showed before. And you make this hole larger and larger. And irrespectively how large you make that hole in the center, you always get the shadow of the same size. The only thing that changes is the strength of the light ring, right? So if the emission concentrates towards the central region, towards this photon orbit, then you're really sharply surrounding the shadow. Once it becomes larger, then you see a larger light ring. Obviously, if you have a light, a large ring surrounded with the center of a black hole, you get sort of a ring from the astrophysics alone, but you still get a shadow. And so that's, I think, the beauty of this. So that's why the nature of black holes really is, encapsulated in the shadow. And you see this also if you do more sophisticated simulations. This is an accretion disk simulation now for a partially optically thin case with an accretion disk, which is also not totally thin. It's actually slightly puffed, slightly thicker. And you look at it, and what you see is, actually you see, for example, here, one bright side on one side, and that comes from relativistic beaming, because that part of the accretion flow goes very fast towards you. You see a dark region, which is close to the shadow here, but not exactly. You have sort of the foreground emission here, which is producing a wedge of light, and you see you see a dark region which is slightly larger than the theoretical shadow. And that again comes from the fact that light can go underneath the black hole up, and then you see the darkness of the universe up there. You don't look into the black hole. Now that changes if you, of course, let the disk rotate. Now let's move the disk around, and you see how the shadow actually changes if you have a thin disk. But if you integrate it from all directions, i.e. you still have an emission that goes all around, even though it's not really isotropic emission, you actually recover a nice shadow again. Yeah, so you see this sharp ring feature of light going around one time around the black hole. You see the light ring, which is bent, and you see the clear shadow. That's well delineated. So what is actually the shadow itself? The shadow is actually a very, very simple effect. It's simply a blocking effect. So just picture a Newtonian dark object, some perfectly absorbing black object that absorbs all the light, embedded in a cloud of optically thin emitting gas. Okay, so what's happening is that if you look towards that dark object, you don't see the light or the gas behind, so you only see a short path length. If you look next to it, you see a higher path length, you see a lower path length. All the light emitted behind the object you will not see, and that will create a dark shadow in this location here. Okay, and that's simply a blocking effect. Light is blocked, and the same is happening in GR. Light is blocked, it ends up in the event horizon. But there are two additional effects, and one of them is the light bending. And so the light will be bent around the object, and so the light that goes around the black hole and actually hits you as an observer will go through more material. Right? In the Newtonian case, it goes straight, but in the GR case, it will be bent, and it will have, pick up more light as it goes. And so it becomes brighter. So that's an increase in the path length. And the second one is that the GR effect, of course, and that's the most important one, the light bending makes this dark region bigger, in fact, by a factor 2.5. And that's pretty much the same as you had for the Eddington expedition, measuring the position of stars around the sun, which were moving due to light bending. It was a factor 2 larger in GR than in Newtonian gravity, and that was the GR effect, the factor 2. And here it's a factor 2.5 in the size of the shadow. So that's how a black hole would look like in Newtonian. You would still see a shadow, right? True. In GR, you would see it a factor 2.5 bigger. And you see actually you get more light path effects, and that's depicted in this picture. Now, what happens if you look towards a black hole? Then you're looking near this characteristic separation, near the shadow essentially, and then light will be bent around, and then you see the entire universe below and behind the black hole. So all the light that's emitted here will be focused and projected towards the observer in a very small region. That is also a GR effect, because you don't have that in Newtonian gravity in that form. Well, if light would go on straight lines in that sense. And that produces a bright region. And so if you make a profile cut through the emissivity, so you calculate here a simple model of isotropic emission, or it's actually a power law emission, but it's a spherically distributed emission around a black hole, so geometrically thick, optically thin. What you then see is a little hump or a bright ring of light emission here, for example. And that is light that has gone around half a time around the black hole. Not a full ring, just half a ring. But that also is a GR effect. And then, if light goes around a full circle, you get a very sharp spike. And if it goes another time, it's another sharp spike. And the more often it goes around, the closer it gets to the true lensed photon orbit and to the true shadow size. But all these orders already contain information. Some people say, oh, you don't see this little feature here. That's true. We see a mix of this broad feature and the narrow feature, but all these features are actually GR features, and they can be used for science, and they contain information about the metric of the object. And so what we do, and so this is very simple models. We of course, like to do much more complicated and sophisticated simulations of accretion flows and jets. Doing full GRMHD simulations with light bending and everything, because really decoupling the astrophysics of the light flow from the light transport would be cheating, right? I see sometimes models where people place a black hole, they make accretion disk, which continue all the way through the innermost stable circular orbit to the event horizon. Then they say, oh, the shadow looks different. It's true, certainly if it's a thin disk, that's certainly true, as I described. But also, this is a pink unicorn. This kind of model cannot work because you're really completely ignoring the effect of the metric on light flowing around a black hole. If you go inside the ISCO, something got to change. And so in all realistic models, actually, they behave very nicely and beautifully to give us nice shadow pictures. That's actually quite amazing. So this here is a model of a MAT solution, a magnetically arrested accretion disk, where you have strong magnetic fields, which actually also produce a strong jet, which is very nicely fitting towards M87. There you have light in a sort of cone surrounding a black hole, and very near the ISCO, and you see beautiful how the shadow is perfectly circumscribed by the emission and the light bending effects. Even if you go to a situation that I describe is not ideal, so an accretion disk, which is geometrically thin, slightly puffed up, you still get something that is close to the shadow within 10 to 20%. So even if you're not quite sure about your astrophysics, we're quite certain that this kind of model doesn't really work. It has to be closer to this model, but even if you would allow for this uncertainty, then you get a reasonably good measurement of the black hole shadow and the GR parameters within the errors. In order to quantify the errors, we made this big GRMHD library in the EHT, calculating 60,000 different images, different astrophysical models, and see what, if we really don't know our astrophysics, how much does this change? And that was done in order to quantify the error. Right? Some people say, oh, it's all astrophysics. You don't know. Maybe the astrophysics is wrong. Well, that's exactly what we try to quantify. We can do the physics with pen and paper, more or less. We could still get a reasonable answer. We just wouldn't be so, clear about what the error bars is. What can we derive from the shadow now? A simple thing is just look at the circularity. I described, that for most parameter spaces, the shadow has to be circular. We've done that, and only within 10%. It can deviate within Kerr, and that's what it does. Our circle or shape or shadow is circular to better than 10%, and that puts actually a limit on the deviation from the Kerr parameter or from the no-hair theorem of order unity. What you can also do is to say, okay, what does the shadow constrain? And what you can show is that the shape of the shadow is actually proportional to the time like component of the Kerr metric. And so that's what you're measuring. Just the size of it measures that component. And you can then ask, if I have non-Kerr metrics, how would the size of the shadow, for example, change? How would, for the given mass, parameters change? And we've fitted, or actually the group of Dimitrios Psaltis has fitted various alternative metrics, actually generalized metrics, not just to a specific theory, just some metrics that deviate from Kerr and try to quantify what the deviation is. And you can actually translate that into post-Newtonian parameters. And if you do this, you can sort of compare that to a traditional test. For example, solar system tests. Solar system tests constrain the first post-Newtonian extension very well, but not the second. And if you assume the first is constrained already, then the EHT constrains the second by orders of magnitude better than any solar system test does. If you allow the first and the second post-Newtonian expansions to change, so just assuming GR fools you, then in fact you get sort of a combination of the first and the second parameter, and you can constrain both parameters. And what you see here is are these contours, and these curves here are actually the same constraints from gravitational waves. It turns out gravitational waves test exactly the same aspects of the metric as EHT does. And so we can do the same tests with GR, with gravitational waves and with the shadow from EHT, and they give the same order of magnitude constraints, but on different mass scales. So that is really complementarity. In all respects, we're testing the same things, just in one case you listen, the other case you see, but you're testing the same GR physics. So let me conclude. I think we see the shadow, and the shadow really is a clear feature of GR. It's fairly independent of astrophysics. Of course, yes, you need to understand in which astrophysical setting you are. If you are optically thin, geometrically thick, you are fine. That you need to understand. Then the shadow will tell you a lot about GR. But that's true for all areas in astrophysics. You know, a little bit of astrophysics you always need to know. You cannot just dream up astrophysics. You have to know in which setting you are. That's true for the Mercury perihelion tests. I mean, you need to know what the gravitational potential of the sun is in order to make any sensible measurement there. So you can never do GR tests without any astrophysics. And I think the astrophysics we do here with the shadow in GR in the Event Horizon Telescope is fairly robust, and we are really able to learn things. And of course we'll be able to learn much more once we go to space in more telescopes on the ground, get higher resolution, and see maybe multiple orders of these rings. And so there's a lot of information hitting in there. And I'm looking forward to those images in the future. Thank you.